One of the first paradigms of computer vision was proposed by David Marr. He described a general framework for understanding visual perception and touched on broader questions about how the brain and its functions can be studied and understood. His work was restricted to 3D interpretation of single static scenes. Marr proposed three levels in his paradigm. The first one, computational theory, which describes what the device is supposed to do. The second one, representation and algorithm, to address precisely how the computation may be carried out. And the final one, implementation, which includes physical realization of the algorithm, programs, and hardware. Let us look at Marr's paradigm in detail. One of the important contributions made by Marr is the representational framework for vision using primal sketch. Primal sketch is similar to a pencil sketch drawn quickly by an artist as an impression, where the most important features of the image are retained and thus helpful in understanding the image. Vision can be interpreted as an information processing task which requires converting a numerical image representation into a symbolic shape-oriented representation. From the primal sketch, which is basically an image with edges, zero crossings, and boundaries, a 2.5 dimensional sketch can be obtained, which can be used to represent orientation and depth of the visible surfaces as well as discontinuities. And why 2.5 instead of 3D? The truth is, from a single viewpoint, it is almost impossible to guess what the object would look like when we see it from behind. Hence, having a repository of 3D models which describe the shapes and their organization using a modular and hierarchical structure can be of use when we are trying to reconstruct a 3D model from a 2.5 dimensional sketch. We can do that by organizing the 3D model description in a hierarchy where the top level is a model which does not have a component decomposition and describes the key aspects of the model. At the next level in the hierarchy, more details are added to the model, and at the lower levels, each individual object's model receives more precise descriptions. For instance, an arm, forearm, hand, and the fingers in this picture. Early research into computer vision resorted to the paradigm of top-down reasoning. For instance, by specifying rules for what an object looks like or watch for its specific pattern. For a few objects in control situations, this worked very well. Imagine, however, trying to describe every object around you from every angle with variations for lighting and motion. It became clear that to achieve even basic levels of recognition would require impractically large sets of data. Alternatively, a bottom-up approach mimicking what is found in the brain is more promising. A computer can apply a series of transformations to an image and discover edges and the objects they imply. The processes involve a great deal of math and statistics, but they amount to the computer trying to match the shapes it sees with the shapes it has been trained to recognize. Then there is this paradigm of 3 R's, which stand for recognition, reconstruction, and reorganization. This paradigm requires us to study the interaction among these 3 R processes and work towards the goal of a unified framework of computer vision. Lot of progress has been made towards the goal of a unified framework for the 3 R's of computer vision. For example, recognition of 3D objects benefits from a preliminary reconstruction of 3D structure instead of just treating it as a 2D pattern classification problem. It is interesting to see how these 3 R's interact with each other and augment each other in solving computer vision problems. Take this example of reorganization assisting recognition using superpixel assemblies as candidates. Using simple vision techniques, we can group similar pixels together and then we can analyze these superpixel regions to recognize objects in the image. Now let us see an application where recognition assists reorganization. Take this example where images are classified directly based on the image intensities. Then we can apply some vision techniques to localize that particular object in the image. This will be useful when you have to deal with multiple objects in a single image. Localization with recognition helps reorganization. For instance, in this image, the pixels belonging to the dog as well as cat are very similar. It's only through recognition that we are able to reorganize these pixels in a better way. Let's look at an example where recognition assists reconstruction. Once we are sure that the object we are looking at is a car, we can create a high-frequency 2.5D reconstruction using the 3D models of the car. When we use all these three R's together, we can attain complete 3D understanding, where we recognize all the objects in the picture, we reconstruct the 3D models of all the objects, as well as understand how they are related to each other using reorganization. Computer vision concepts can be broadly categorized as low, mid, and high-level vision techniques. Low-level vision constitutes of image processing techniques, feature detection, and matching and early segmentation. Mid-level vision is where things start to come together, attributing meaning. High-level vision tasks are the algorithms which make sense of the visual content and make computer vision live up to the capabilities of human vision. We shall go over these concepts in much more detail over the next few lectures. But let me briefly introduce these concepts to you. Low-level vision or early vision considers local properties of an image. For instance, this image has several edges. When we move to mid-level vision, so that's where we start to group things together. Preliminary analysis on these pixels tells us there's an object as well as a background in this picture. Now moving on to the high-level vision, that's where we identify what's there in the image. In this instance, it's an aeroplane.